Thank you for joining us. My name is Joel Staller, and today I will discuss how advanced polymer technologies are implemented in the most vital e-mobility systems. Additionally, we will discuss the intricacies involved in the guiding properties used to qualify thermosetting compounds and how these properties will improve power, efficiency, and longevity for e-mobility applications. First, let me tell you a little about Epic Resins. Epic is located in southeastern Wisconsin. We have been a formulator and manufacturer of epoxy and polyurethane materials since 1958. This timeline highlights Epic's decades of involvement in electrical applications, starting with power distribution in the 60s to flyback transformers in the 70s, fast forwarding to the development of current advancements in e-mobility technology. With 65 years of experience in polymer formulation, we have gained a deep understanding that each application is unique and that technologies are constantly advancing and pushing the limits of polymers. Our experienced team of chemists has a philosophy of true research and development. We are constantly developing new polymers with advanced properties to innovate e-mobility systems, pushing the limits of power and efficiency within the electrification industry. We minimize your investment risk by testing all products to the highest standards. Our production and warehouse facility includes approximately 85,000 square feet. This houses over 10 high-speed dispersers, multiple vacuum pumps, and our farm of raw material bulk tanks. Epic's core polymer technologies include epoxy and polyurethane thermoset materials. We have over 3,000 epoxy and polyurethane formulas and service over 1,500 customers worldwide on 6 continents. Epic Resins is ISO 9001 and 14001 certified. Our focus today is on 3 highly engineered systems that drive e-mobility innovation: electric motors, power electronics, and sensors. In the dynamic e-mobility landscape, these 3 systems play integral roles, and one crucial element binds them together: advanced polymer technologies. As the industry accelerates, the need for innovative polymer solutions to maximize performance, reduce stress, and exceed safety standards becomes paramount. Among these 3 systems, the electric motor system emerges as a transcending focus, commanding attention from engineers, marketing strategists, and the discerning eye of consumers. This unifying system serves as both a marketing canvas showcasing power and an engineering accomplishment harmonizing size, energy density, and efficiency, all while simultaneously engaging the consumer to embrace the innovation of the era of electrification. The e-mobility industry places a premium on an electric motor's ability to carry a high current without overheating. Polymers are an integral part of the thermal management system, which lowers the operating temperature of electric motors, resulting in higher power output, longer motor life, and better reliability. This is due to the change in resistance of copper wire when heated and is better known as the temperature coefficient of resistivity, or the TCR. The TCR for copper is 0.39% at 20 degrees C. Simply put, a 0.39% increase in resistance of a copper wire in an electric motor can have drastic downstream effects on power wattage of the motor. For this reason, thermal management is vital. Thermal management is addressed by multiple means, but typically either oil cooling or heat sink cooling. Thermoset polymers are a fundamental part of the thermal management equation. The most robust techniques for protecting electric motor conductors are utilizing thermosetting polymers for secondary insulation systems and thermal potting compounds. We will start by discussing secondary insulation materials. A secondary insulation impregnates and bonds the conductors together, which builds a solid, cohesive unit of conductors. This improves the longevity of the motor by eliminating independent wire movement as well as reducing motor noise. Secondary insulation must have an excellent adhesion to the primary insulation and excellent thermal and chemical resistance. Adhesion is vital to maintain the conductors as a cohesive unit. Thermal resistance is important so that the polymer maintains its adhesion and structural integrity for the longevity of the electric motor system. We have developed ProPreg E240 secondary insulation to accomplish these properties. The unique surface tension of ProPreg E240 significantly improves the adhesion to PEEK-coated conductor wire and slot liners compared to the leading polyester. The analysis conducted to test adhesion was a 180-degree peel test. As you can see in the illustration, a PEEK film is adhered to the metal conductor substrate using ProPreg E240 or polyester insulation. The PEEK film is then pulled at a 180-degree angle while the metal conductor is held in place. In the 180-degree peel test, you see in the graph that ProPreg E240 obtains at least double the adhesion compared to the leading polyester. Adhesion alone does not assure success as a secondary insulation. Adhesion must be maintained when exposed to elevated temperature conditions and applications using oil cooling. For secondary insulation materials, adhered wire bundles are tested using IEC 61033. These bundles are exposed to elevated temperature ATF and elevated temperature ATF vapor at 150 C. Samples are then conditioned for a total time interval of 2,000 hours. The integrity of the adhesion is then tested by the fixture in this illustration. This fixture measures the force required to break the center wire free, which mimics the wire in the slot. From the data collected, you can see that after 2,000 hours at 150 C exposure immersed in ATF, over 91% of the original adhesion is maintained, and over 97% maintained for ATF vapor exposure. Additionally, during the analysis, separation took place between the polymer coating and copper wire, while the bond between the varnish and the polymer coating remained intact. The results indicate that the varnish polymer bond strength was greater than the polymer coating tensile strength and the polymer copper bond strength. Accomplishing high adhesion strength coupled with excellent chemical resistance gives a tremendous advantage for advanced motor performance in electrical motor systems. Electric motor system protection includes motor potting. Electric motor potting compounds are used for applications that require complete encapsulation of the gap and the end turns, completely protecting the motor conductors and placing them in intimate thermal contact with the exterior of the case. This type of engineering accomplishes two properties for the motor. One, permanent insulation of the motor conductors for heavy-duty and submersible applications, and two, gives a high degree of thermal contact with the heat sink to dissipate heat and improve efficiency. In heavy-duty industrial applications, potting is the only choice to ensure protection, longevity, and excellent thermal performance. There are multiple topologies where motor potting is essential. For example, axial motors are designed for enhanced performance, and one of the benefits is their direct hub installations. This location in an EV exposes the motor to greater environmental stresses, including water and vibration. Completely potting the axial motor conductors gives them excellent protection against these environmental stresses. In radial motor IPM SYN RM applications, the permanent magnets need to be securely fastened into the rotor. Potting compounds will permanently fasten the magnets to the correct position, which creates precise magnetic flux location for optimized electrical and magnetic field coupling. This yields maximum torque and efficiency for the motor. When choosing a motor potting compound, thermal stability and thermal conductivity are two of the most vital properties. Thermal conductivity is important since dissipating heat reduces operating temperature and thus extends the life of the motor and its vital components. Thermal stability ensures efficiency and longevity by maintaining the polymer's properties over extended periods of thermal exposure. Monitoring weight change and hardness change at elevated temperatures gives a great comparison when determining the stability of a motor potting compound. In this example, we have thermally stressed samples of EPIC 0218 EV epoxy and a leading polyester at 150 C for 500 hours. When you evaluate weight loss and hardness change, you can see 0218 EV maintains its weight more consistently than polyester. The greater stability of the O218 EV epoxy is due to the better stability of its molecular structure compared to polyester. More specifically, polyesters have lower cross-link density and molecular bond stability when compared to the chemistry of O218 EV epoxy. Over the life of a heavy-duty electric motor, this thermal breakdown can lead to cracking and wear exposure, which can both cause catastrophic failures of the motor. In conclusion, the e-mobility industry depends on advanced polymers to protect copper wires for efficiency and longevity of the electric motor system. Now we will investigate how the e-mobility industry utilizes polymers to enhance power electronics. Power electronics encompass a wide array of individual components including inverters, bidirectional inverters, DC to DC converters, battery management systems, battery chargers, both onboard and external, and advanced driver assistance systems. As e-mobility power electronics evolve, manufacturers are finding efficiency and convenience in combining these systems into one architecture and location. Efficiency in multiple uses of the same components as in bidirectional inverters, and convenience in housing multiple components in one enclosure to reduce cabling requirements and coolant flow to one epicenter of the vehicle. Individually or combined, these power electronics process an extraordinary amount of electrical energy while simultaneously orchestrating precise control over a multitude of components. Precisely processing these high levels of energy requires a delicate balance of properties to yield safety, efficiency, and longevity. It's paramount to choose the appropriate advanced polymer that is capable of simultaneously dissipating heat, mitigating thermal cycling, insulating high voltages, and protecting against flame propagation. Some of the highest profile properties used to enhance the performance of power electronic polymers include flammability rating, thermal conductivity, thermal cycling, and dielectric strength. Improved performance has evolved from enhancements made at the molecular level to propel macro polymer level performance to meet the demands of power electronics. We will be diving into each of these properties to give you a better understanding of how each property is attained, optimized, and affects the performance of your power electronics. Power electronics are essential for EV performance. These components generate heat, handle high currents, and may be located close to flammable substances like fuel or coolant. Ensuring that these components are made from materials with appropriate flammability ratings helps mitigate safety risks. The flame rating of a polymer is an indication of a polymer's ability to be ignited, support a flame, and self-extinguish. There are many flame ratings for polymer systems. The most common flame ratings are defined by Underwriters Laboratory, or UL. In the context of power electronics for e-mobility, understanding flame ratings is crucial to preventing fires and enhancing overall safety. Material selection plays a pivotal role in achieving desired flammability ratings. Engineers and manufacturers subject materials to various tests, such as the UL 94 flammability test. This test assesses a material's ignition resistance and flame propagation characteristics. The UL 94 flammability test is a series of classifications that define the flammability properties of polymers. The most common are HB, V2, V1, and V0. HB indicates a horizontal burn test, where the specimen tested is placed horizontally as shown in this illustration. The prefix V indicates a vertical burn test, where the sample is placed vertically as shown in this illustration. Here is an example of the UL 94 V0 test using EPIC RM 2018. The flame is incident on the bottom of the vertical sample for 10 seconds and then pulled away. When it extinguishes, the flame is put back under the sample for 10 seconds again and then pulled away. The after flame time after each burn is recorded. As you have seen, the potting compound is burned as described and extinguishes in less than 10 seconds combined for both burns. This table outlines the test results for classification within the UL 94 series. Though all the criteria of the test are important, the two most critical results are the after flame time for each incident of the flame and ignition of the cotton. Specifically, for V0, the after flame time must be below 10 seconds and no drips can ignite the cotton bundle. As discussed earlier, heat is also an enemy of the efficiency of e-mobility power electronics. As each of the big three e-mobility systems is developed, engineers of each of these systems convene to manage the thermal energy to and from these systems. Thermal systems in e-mobility are important in managing heat and maintaining peak operating conditions for the power electronics. Dissipating heat from the power electronics to the thermal system is vital to improving the component efficiency. The conduit between the power electronics and the thermal system is thermally conductive potting compounds. Thermal potting compounds vastly improve the efficiency of the thermal system, and this yields the greatest results in thermal management of the power electronics. The thermal conductivity of a potting material is a measure of a material's ability to conduct heat. Heat is a form of kinetic energy. Improving the particle kinetics of the potting compound is key to improving thermal conductivity. The thermal conductivity of a polymer is primarily dictated by the type, size, and loading of a thermally conductive mineral in the polymer. Optimizing the loading and size of the thermally conductive particles improves particle contact, which in turn enhances particle kinetics and hence thermal conductivity. At Epoxy Resins, we leverage our laser diffraction particle size analyzer to optimize this property for our customers. As you can see in this example, 3 separate particle size grades of mineral filler have different size distributions. When we optimize the ratio of the 3 grades, you can see we get an overlap of the sizes to fill the interstitial space more completely between the particles. Optimizing the loading of interstitial spaces improves particle contact kinetics, thermal conductivity, and viscosity. This infrared time-lapse video gives you a visual representation of 3 polymers with different thermal conductivity. These 3 products are Epoxy S7524, Epoxy RM2018, and Epoxy S7527. S7524 on the bottom left has low thermal conductivity. RM2018 on the bottom right has medium thermal conductivity. S7527 on the top has high thermal conductivity. The infrared image shows as the pucks are heated from the bottom, you can see that the S7527 gets hot faster than the other 2, indicated by the yellow color. Obviously, this shows that it is pulling heat from the hot plate faster than the S7524 and RM2018. Choosing the correct thermal potting compound for your power electronics will improve efficiency and longevity by increasing heat transfer, resulting in reduced thermal cycling. Several factors impact how potting compounds perform under thermal cycling. These include the type of polymer used, the filler materials added to enhance thermal conductivity, the coefficient of thermal expansion, and the glass transition temperature, also called TG. Balancing these factors is crucial when designing potting compounds that can handle the demanding cycling condition of power electronics. Thermal cycling refers to the process of subjecting electronic components to alternating cycles of high and low temperature. In demanding e-mobility environments where temperature fluctuations can be extreme, it's essential to use potting materials that can withstand these conditions while also protecting the integrity and efficiency of the power electronics. Potting compounds based on epoxy and polyurethane chemistry are used to encapsulate and protect delicate electronic parts from moisture, vibration, and mechanical stress. However, the repeated thermal cycling experienced by power electronics can introduce challenges. As the temperature changes, materials can expand and contract, potentially leading to mechanical stress on the components within the power electronics. Over time, this stress could cause cracking or delamination, exposing the power electronics to environmental factors. To determine how a material responds to thermal cycles, we evaluate the glass transition temperature and coefficient of thermal expansion. The TG is the temperature when a material changes from a rigid glass-type material to a soft, pliable material. The coefficient of thermal expansion, or CTE, is the rate of expansion over a temperature range. We evaluate TG and CTE using a thermal mechanical analyzer, also called a TMA. This measures the height of a sample when ramped through a temperature range. The image we are showing here is a graphic result of a TMA. At the low temperature portion of this graph, on the left, you see the pre-TG CTE from -40 to 0 degrees C. As the temperature increases to the right, we see an inflection point on the graph at about 60 degrees C. This is the TG. Below this temperature, the polymer is considered a rigid polymer, and above this temperature, the polymer is a soft, pliable polymer. To the right of the TG, you see the post-TG CTE, which is higher than the pre-TG CTE. It is important to understand where the TG of the polymer is relative to your operating temperature range to reduce component stresses that occur in this thermal transition. Before potting compounds are integrated into power electronics, manufacturers subject these compounds to accelerated thermal cycling tests to simulate the conditions they'll face in the real-world environments. This helps identify potential weaknesses and guides the refinement of the compound's formulation. We utilize our in-house thermal chamber to run life testing on actual customer parts. Our in-house thermal chamber allows us to test your potted electronics parts at your specified temperatures and humidities. The chamber has a temperature cycling range of -70 to 180 degrees C and a humidity cycling range of 15 to 95% relative humidity. These parameters are then used to set your desired testing protocol using the PLC control on the thermal chamber. E-mobility power electronics are evolving into sophisticated systems with intricate electrical components and high voltage systems in smaller and smaller packages. Ensuring that these components remain isolated from each other in these condensed architectures is essential to preventing electrical failures, fires, and potential hazards. This is where potting materials with high dielectric strength come into play. When a material's electric field surpasses its dielectric strength, it undergoes dielectric breakdown. This breakdown can lead to electrical arcing, short circuits, and damage to surrounding components. For EV electronics, where safety and reliability are paramount, minimizing the risk of dielectric breakdown is a primary concern. Polymer insulating materials are an essential component in EV electronics in preventing dielectric breakdown due to their inherently high dielectric strength, but selecting the right material with the appropriate properties is critical. The dielectric strength of a potting material is influenced by several factors, including its composition, molecular structure, and any additives present. Before integrating a potting material into power electronics, thorough testing of the dielectric strength is essential. At Epic Resins, we are an industry leader in the formulation of innovative potting compounds with high dielectric strength. Our R&D chemists are continuously developing new potting compounds with unique molecular structures to withstand the increasing voltages used in power electronics while still maintaining your desired mechanical and thermal properties. We understand the urgency within the industry to evolve to higher voltages, and we have developed products to suit these needs. In conclusion, choosing the correct polymer for flame rating, thermal conductivity, thermal cycling, and dielectric strength ensures the longevity and safety of your power electronic devices. We will now discuss how the e-mobility industry utilizes advanced polymers to protect sensors. Sensors are extremely important and encompass many of the greatest innovations e-mobility is giving our society. Autonomous features like lane diversion and autopilot make the reliability of sensors vitally important. Sensors are often placed in critical but inconspicuous locations to feed information to the vehicle's data center. In many cases, these inconspicuous locations are at the perimeter of the vehicle, which gives sensors more severe environmental exposure. This exposure makes sensors much more vulnerable to moisture, high vibration, and impact potential, making adhesion critical to longevity. The adhesion of a potting compound in a sensor is the first line of protection from the exterior environment. A failure in adhesion can cause a direct leak path, resulting in sensor failure. Specifically, adhesion refers to the strength of attachment between two different materials. In the realm of e-mobility sensors, strong adhesion is essential for various reasons. Components need to maintain their adhesion integrity to dissipate heat effectively, maintain electrical insulating properties, and protect sensitive electronic components. When the proper material is chosen, it enhances the sensor's ability to maintain performance, ensure longevity, and increase efficiency. Achieving adhesion to the multiple substrates that occur in sensors requires unique chemical formulations. At EPIC, we formulate from a molecular structure to property relationship in order to maximize adhesion to your substrate. Choosing the correct molecular structure will modify the surface tension of the material to wet out the substrate to achieve adhesion. In most sensor applications, the vital surface to bond to is the case material. Once the correct molecular structure is chosen, an adhesion test analysis is performed to determine adhesion to the subject substrate. When testing the adhesion of a potting compound, an excellent test method is a modified version of ASTM D1002 lap shear adhesion test. This is a robust test method that is effective at determining the relative adhesion to multiple substrates. Though this test method calls out for metal bonding, any substrate like ABS, nylon, polycarbonate, etc. can be tested. The test is conducted by bonding two flat pieces of substrate by a 1 inch by ½ inch overlap. This coupon is then pulled at 0.05 inches per minute on a universal testing instrument. The maximum force attained at the failure of the bond line is divided by 0.5 inches of the overlap area to determine the lap shear adhesion in PSI. The sensors located at the periphery of the automobile have some of the greatest exposure to moisture. This exposure is only a problem when that moisture finds its way into the sensitive electronics of the sensor. Potting materials are the best way to protect sensitive electronics from harsh outdoor environments. Choosing the correct encapsulant is important. Depending on the chemistry, there will be different levels of protection for the sensor. This difference is in the way water interacts with the chemistry of the potting compound. The most common type of water interaction on a sensor is water vapor and humidity. To understand this, we need to better understand how water vapor exists in our environment. Water vapor is all around us, every day, all day. This is based on the partial pressure of water in the atmosphere, also known as the relative humidity. This partial pressure is actually energized water molecules bouncing around like balls in a racquetball court. A material's ability to contain these water molecules is the water vapor permeability of the polymer. The most common test used to measure this property is ASTM E1653. This is the fixture used to conduct ASTM E1653. This illustration shows how the tests function to measure the water vapor permeability of a polymer. There are some variations of the test, but for simplicity, we will illustrate method and condition A, where water is placed in the cup and the cup is placed in a desiccator with near zero relative humidity. As water vaporizes in the cup, it interacts with the polymer. Depending on the polymer, different levels of these water molecules will attach to the surface and dissolve in the polymer. The water molecules will be drawn to the outside since the desiccant has lower relative humidity. Because polymers will have different water vapor permeability, varying amounts of water will be drawn out of the cup as illustrated in this graphic. This is a side-by-side comparison of EPIC 7202-05 and an industry-leading silicone potting compound. This shows how different polymers will have different water vapor permeability. As the exterior of a sensor is exposed to humidity, it begins to accumulate in the sensor. This causes degradation of the electrical performance of the circuit until it fails. Since humidity is ubiquitous, it is essential to utilize potting compounds for the best protection from water circuit failures. Advanced polymer solutions bridge the gap between function and optimization in e-mobility applications. At Epic Resins, our experienced team can help you choose the polymer that is the best fit for your application to maximize performance by optimizing your thermal system, reduce component stress caused by increased voltage and power density, and exceeding safety by protecting against fires and improving component reliability. Our advanced polymers have the versatility to delicately balance the properties needed to push e-mobility to be the most efficient, reliable, and ubiquitous form of transportation society has ever known.